session, I'm going to look at degenerate kernels. A kernel, K of ST, is termed degenerate if it can be represented in the form of a finite sum of pairwise product. I'm going to say that a kernel K of ST is said to be degenerate if it can be represented in the form of finite sum of pairwise product function. That is one of the function of only S and the other function of only T. So that's in mathematically I'm going to say that degenerate kernels is K of ST should be equal to A of what? Let's say A1 of S, B1 of what? T, plus A1 of A2 of S, B2 of T, plus A3 of S, B3 of T, plus plus AN of S, Bn of T. And so we are saying that the kernel is a sort of a finite sum of pairwise product functions. So this is the same as summation of what? A I of S, B I of T, and I is running from 1 to n. That makes it to be a finite sum. So this is the definition for degenerate kernels. Okay, I'm going to use this to solve a Fredholm's integral equation. So given a Fredholm's integral equation, y of s to be equal to f of s plus lambda integral from a to b k of st y of t dt. Now let's substitute this kernel, which is called a degenerate kernels, into this Fredholm's integral equation. So we're going to have y of s to be equal to f of s plus lambda integral of a to what? B. In a big bracket, k of st, a1 of s, b1 of t, plus the next term a2 b2 of t, a2 of s and b2 of t, plus a3 of s, b3 of t, plus plus an of s, bn of t, then y of t dt. You can see that the function of s is not affected by the integral sign because it's acts as a constant. So you can open up this kernels, this equation, to get y of s to be equal to f of s, then plus lambda integral of a to b, then the first term a to b, then a1 of s, b1 of t, y of t to b dt, plus this lambda in the second term, so plus lambda integral of a to b, a2 of s, b2 of t, y of t dt, plus lambda and the integral sign, then the third term, so lambda integral of what? A to what? B, a3 of s, b3 of t, y of t, dt. And let's take the nth term. I'm going to have our lambda integral of what? A to what? B. Then the nth term is what? An of s, bn of t, then y of t dt. Can still then let's bring all the functions of what? S out. A1 of s, a2 of s, a3 of s, then an of what? S. Let's bring all of them out. I'm going to have our y of s to be equal to f of s plus lambda a1 of s integral from what? A to b. Then b1 of t, y of what? T dt plus, then we will bring what? This a2 of what? S out. We will have lambda a2 of s integral from what? A to b, b2 of t, remaining y of t dt plus this term. So we can just jump to the what? The last term plus, because the last term is of lambda of what? An plus lambda of what? This an of s integral from what? A to what? B. Then bn of t, y of t dt. Now let's write this term 1, 2, 3. This term in the form of what? A combined form, in a series form, in a summation form. So the y of s becomes y of s to be equal to f of s plus lambda. And lambda is here. Then I have, you can see a1, a2, a3, a4 up to an. I'm going to represent it by summation of ai of s, that is 1, 2, 3 continuous. Then I have integral of what? A to b, then b1, b2, b3. So it becomes integral of a to b, then bi of t, y of t dt. So this the series form where I runs from 1 to n. Now, as we did in the exact method, after doing this, we represent the functions with only the t with a constant. So we are going to do same here. So let's ci to be equal to integral of a to b, bi of t, y of t dt. Ci to be equal to this. And let's substitute this ci into this equation. I'm going to have now y of s becomes f of s plus lambda summation of I to be equal to 1 n. Then ai of what? S times what? Your ci. Let's note it here. If I have ci is the same as cj, because if I change this index to j, we will still have the same thing. Ci is the same as cj. So I will be using this interchangeably. So if I don't use the c, I will use the cj. Now we have this equation. We have our ci to be equal to what? Integral from a to b, bi of t, y of t dt. And this is our y of t. Now we need to change the s here to what? T. So our y of t becomes f of t plus lambda summation of what? I to be equal to 1 and AI of t ci. So this is our y of t. And we have to substitute this y of t into this equation. So our ci is equal to integral from a to b bi of t to bracket. Now, for this equation to communicate better with this equation, let's change the i's here to j. So some so it becomes aj of what t and what cj. So this becomes f of t plus lambda summation of I to be equal to 1, j to be equal to 1 to what? N. Then aj of t cj. Then my what? dt. Now let's open up this equation. You can easily see that this integral from a to b, bi of t, then m of t, then what? dt. I'm going to have my ci to be equal to integral from what? A to b. The first term, which is bi of t, then f of t dt. Then the second term, bi of t times what? This term. So I can rewrite this as plus integral of a to b, then summation. That let's take the bi of t under the summation sign. So sum of what? Bi of t, then aj of what? T. Where yes, I, j to be equal to 1 to what? M. Then the cj is here. Cj, then what? dt. Now, there is a lambda here. So, alright. So there's a lambda here. So lambda have to come outside. There's a lambda in this term. So let's put our lambda here. Let's put our lambda there. Now we're having this equation. Now I'm going to let our let's let jij, which is a matrix. Jij like is a tensor in a tensor form. A matrix in a tensor form. So jij to be equal to integral of a to b, then bi of t, then ai of aj of t, then my dt. Then let's let this term to be equal to fi. Let's represent it by fi. Fi is a vector in its a tensor form. So here becomes integral of a to what? B, which is the first term. Bi of t, f of t, dt. Now let's rewrite this equation. I'm going to have ci to be equal to fi plus lambda summation of aij, then cj I, j to be equal to 1 to what? N. By answer summation, since this one is a tensor, I can easily draw what? The summation sign for more tensor. So I'm going to have ci to be equal to fi plus lambda jij, then cj. I said we should let us ci to be equal to what? Cj. And so this side, let's change this side to what? Cj. So I'm going to have cj to be equal to fi plus lambda jij, then Cj. I mean the Cj is here inside of the equation, and this is a constant. Since a constant, we can factorize, we can add a connected data function to it. Delta ij cj, and so we can bring this one to the other side, which is minus lambda jij cj to be equal to fi. So this one here becomes delta ij minus lambda jij cj to be equal to fi, and this is a connected data function, and it says that delta ij is the same as, it is 1 when I is equal to j, and 0 when I is not equal to j. So let's generate a system of equation from this relation. When we have I to be equal to 1, we're going to have, and j to be equal to 1, we're going to have 1 minus lambda j 1 times what? C1. Now here is a column, the j is a column, so it runs through. So the next one is delta ij. When I is 1, but j moves to 2, is here becomes what? 0. So we're going to have minus lambda j1 2, then what? My c what? 2, plus dot plus the n term when j is n and I is still 1, that's it. So we are going to have minus lambda j 1n, then what? Cn to be equal to I is what? 1, so we're going to have f1. And let's move to when I is equal to 2. When I is equal to 2, we are having 2 here, and j is 1, so here is 0. So I'm going to have minus lambda j of what? 2 1, then c what? 1, j is 1. Then let's move to the next one. I'm going to have, when here is I is already 2, then j moves to 2. We're going to have 2 then here is what? Connected data function becomes 1. We're going to have 1 minus lambda j 2 c 2 plus dot. The n term becomes here I is 2 and j becomes n. They are not equal, so here becomes 0. So you're going to have minus lambda j 2n cn to be equal to fn. Our next one becomes when I is 3 and we start from j equal to 1. We would have minus lambda j 3 1, because 3 and 1 are not equal, so the connected delta function here becomes 0. And then c1, j is what? 1. J runs from 1 to 2 again. We're going to have here to be what? 0, because here is 3 and 2. Connected delta function becomes 0. So here becomes minus lambda j of what? 3 2, then what? J is 2, then becomes c2 plus dot. The last term becomes minus lambda, and so here becomes 3 and it's not equal to, they are not equal, so here becomes 0. Then here becomes minus lambda what? 3 what? N, j 3n, and having cj here, cj is what? N, so cn to be equal to what? Well, here is f2 rather. Here becomes f, I is what? 3, so here becomes f3. So if we do it up to the nth term, we're going to see that when I is n, we're going to have minus lambda j of what? J of what? n1, jn1. That means when I is n, I'm going to have what? N1, then c1 here. And the next one, we're going to have minus, still minus, because we're having n and what? We're going to have n and what? 2. The connected delta function here becomes 0. So minus lambda g of what? N what? 2. J n 2. Then c what? J is what? 2. C2 plus dot plus into bracket. We're going to have up to the n term. So when j is n and I2 is n, I'm going to have the connected delta function to be 1. So 1 minus lambda g of what? N, then what? C n. So 1 minus lambda g of n times what? J is what? N, so C n. So how to equal to what? F of what? N. So this is our m equation. So this is a system of equation. Let's put it in a matrix representation. Let's do this in the matrix representation. The matrix representation, we're going to have the first term, which is lambda minus 1 minus lambda j11 in our first entry. 1 minus of lambda j11. Moving on to the next one, having minus lambda what? j12. j12. Up to the n term, we're going to have minus lambda jn1. Then let's come to this equation. We're going to have minus lambda j21 as a first entry on the second row. And our next term on the second row is 1 minus lambda j22. So we're going to have 1 minus lambda j22. Alright. Okay, yes. Minus lambda j what? 1n. So yes, another what? 1n. How to dot. The last term there becomes lambda minus lambda j2n. So here becomes minus lambda j2n. On our third rule, we're going to have minus lambda j31 minus lambda j32 and minus lambda j3n. So minus lambda j31 minus lambda j32 up to what? Minus what? Lambda j3n. And our last term, and so we do this until we get to our last term, the m term. You're going to see that yes, minus lambda jn1 minus lambda jn2, and here becomes 1 minus what? Lambda jnn. So minus lambda jn1 minus lambda jn2 up to the last term there is what? 1 minus lambda jnn. So in a big equation, in a big matrix, then you can write our C1s here. That means C1, C2, n up to Cn. That's our unknowns. So C1, C2, C3 up to Cn to be equal to this F1, F2, F3 up to Fn. F1, F2, F3 up to Fn. So this is a system of equation. So you can easily solve this to find for the unknown C1, C2, C3, Cn. You can use any method, but let's use a suitable one, which is known as the Kernels rule. So to solve for this system, so using the Kernels rule, we let's find for the determinants of this matrix, and let's name this as d lambda, d of lambda to be equal to the first entry is 1 minus lambda j11, then minus lambda j12 dot dot dot, then what minus lambda what j1n. The next entry becomes what minus lambda j21. Here becomes minus 1 minus what lambda j22. And here becomes what minus lambda j2n. And here we have minus lambda j33. j31 minus lambda j31. The next entry becomes minus lambda j32 up to minus lambda j3n. The last rule becomes minus lambda jn1, then minus lambda jn2 up to the nth. The nth having 1 minus lambda jnn. Then this is the determinant that you are going to look for. So yeah, so by Kernels rule, I'm going to say that we're going to find for the C. So let's say Cj will be equal to the determinant. Like if you want the C1, if you want to solve for C1, you have to represent it here by the first column and find the determinant. Then you divide that determinant over what? This determinant. We're going to say that Cj is the same as, we're going to name that determinant as dj of lambda divided by what? This determinant, d of what? Lambda. So for that, if you operate on it using the Kernels rule, you are going to see that it is the same as finding summation of I, j of aij, then this fi's divided by d lambda. So this the combined form for the Kernels rule. Now, so this is our Cj. So this is the solution to what? This constants, the C's. And had our y of s to be equal to f of s plus lambda of what? Summation of I equal to 1 to infinity ai of s ci's. But let's change the ci to cj because we're having cj here. Oh, okay, alright. So we're going to have y of s to be equal to f of s plus lambda summation of I to be equal to 1 to n. Then ai of s. Then this is my what? Cj. So let me substitute this one to this side. I'm going to have y of s to be equal to f of s plus lambda summation of I to be equal to 1. And say to n. Since I'm making this one here, let's add another summation to it. J to be equal to 1 to what? N. AIS, then A, this AIJ, then FI divided by what? d of what? Lambda. And we said that the fi is same as integral of what? A to b, bi of t, f of t. So let's substitute this one into this equation. I always have y of s to be equal to f of s plus lambda. So I can easily bring the integral first. So integral of what? A to b. And they say fi is the same as what? Integral of what? A to b, bi of t, f of t dt. So we are putting this one into this side. And I'm going to see that here is the same as summation of I to be equal to 1 to n, summation of j to be equal to 1 to n. Then my what? Ai of what? T. Then what? Bi of what? Bi of t. No, this Ai of s. Sorry. Ai of s. Then Aij is a function of lambda. Aij is a function of lambda. Then what? I'm having a f of what? T dt. Now add it to it. F of t dt. And yes, divided by what? D of what? Lambda. Now let d of s t lambda to be equal to the whole of this. Summation of I to be equal to 1. Summation of j to be equal to 1 to n. Ai of s, then bi of t, then ai of j lambda. So we have to substitute this into this equation. So you can easily see that y of s is equal to f of s plus lambda. There is d of what? St lambda. So integral of what? A to b, d of st lambda divided by what? D of what? Lambda. And here is what? F of t dt. Let's name here as gamma of st lambda to be equal to this side. D of st lambda divided by d lambda. And we are going to name this as a resolvent kernel, as we did in the approximate method. So this is the same as our resolvent what? Resolvent kernel. So let's substitute this into this equation. So substituting the gamma to this side, I'm going to have y of s to be equal to f of s plus lambda integral of a to b. The gamma of st lambda, then your f of t dt. So this we know for what? We know how to solve for the gamma of st lambda, and the free term is also known. Then from the system of equation, the system given, you can easily solve for what? This function y of s, which will be the solution for the integral equation, which has a degenerate kernel. Which has a degenerate kernel. Alright, so this is the end of this session.